Have you ever stopped to think about our planet's weather? Not as just random, chaotic stuff that happens, but as one single, giant, interconnected engine? A massive machine, powered by the sun, that's constantly whirring and churning all around us. Well, today we're going to pop the hood and break down exactly how that engine works.
Okay, so before we get into the nuts and bolts, we have to get one thing straight, because people mix this up all the time. The difference between weather and climate. And honestly, it's pretty simple. Weather is what's happening right now. It's the outfit you pick out for today. Climate? That's your entire wardrobe. It's the average weather over decades, the overall pattern you can expect, year in and year out.
All right, so every engine needs fuel to run, right? For Earth's weather engine, that fuel is temperature. And the source of all that energy? It all starts with our sun.
Now, there's a great word for this: insolation. It's just the scientific way of saying the sunlight that actually reaches Earth and heats things up. And what's wild is that we only get a teeny tiny fraction of the sun's total energy. But that tiny fraction, it's more than enough to power our entire planet's weather system. Now here's the absolute key to the whole thing. The engine doesn't start because of the heat itself, but because that heat is uneven. Since the Earth is a sphere, some parts get blasted with direct sunlight while others just get glancing blows. This uneven heating, that's the spark that ignites the whole engine.
And you can see how this creates these huge, distinct temperature zones. Right around the equator, where the sun is most direct, you get the hot, torrid zone. A bit further out, you have the milder, temperate zones, where we get seasons. And then way up at the poles, where the sunlight barely skims the surface, you get the freezing, frigid zones. This fundamental temperature difference is what gets the ball rolling.
So we've got our fuel, that uneven heat. But fuel just sitting there doesn't do anything. You need a force to turn that heat into actual movement. And for our weather engine, that force is air pressure. So let me ask you a little riddle to help wrap your head around this. What weighs more than a ton, but you don't feel it crushing you right now? The answer, believe it or not, is the column of air that's stretching from the top of your head all the way to the edge of space. Air actually has weight, a lot of it, and we call the force of that weight atmospheric pressure. The only reason we're not all flattened like pancakes is because that pressure is pushing on us from all directions equally, and our bodies are pushing right back.
Now, this is the golden rule. If you remember one thing, remember this. Hot air expands, it gets lighter, and it rises. Think of a hot air balloon. That creates an area of low pressure. Cold air does the exact opposite. It shrinks, gets denser, and sinks. That creates high pressure. And here's the most important part. Air will always move from an area of high pressure to an area of low pressure. It's constantly trying to find balance. And this works with altitude, too. You've probably felt this yourself, right? When your ears pop as you drive up a mountain. At sea level, there's a huge column of air on top of you, so pressure is high. As you go up, that column gets shorter, there's less weight, and so the pressure goes down. Okay, so let's recap. We have our fuel from the temperature differences, and we have our driving force from pressure differences. So what happens when you put them together? You get the moving parts of our engine. The gears start turning, and we call those gears winds. And here it is, the whole concept in one simple diagram. That cold, dense air sinks, creating high pressure. The hot, light air rises, creating low pressure. Wind is simply the air flowing across the surface to fill the gap, always rushing from high to low. That's all wind really is. Now, just take that same simple idea and blow it up to the size of a whole planet. You have a massive low-pressure zone at the hot equator and two high-pressure zones at the cold poles. This sets these gigantic, predictable wind systems in motion, like the trade winds and the westerlies. These are forces so reliable that ancient sailors built entire empires by riding them across the oceans. But what's really cool is this engine doesn't just work on a planetary scale. If you've ever been to the beach, you've felt it. During the day, the land heats up way faster than the water. This creates low pressure, which pulls in that nice, cool sea breeze off the ocean. Then at night, the whole thing reverses. The land cools down faster, and a warmer land breeze flows back out to sea. It's the same engine, just working on a local scale. Okay, so our engine is humming. We've got heat as fuel, pressure as the force, and winds as the moving gears. But what does this massive machine actually produce? Well, you add one more key ingredient, moisture, and you get the final product: clouds, rain, snow, you name it, precipitation. It's really a three-step process. First, Evaporation. The sun's heat turns liquid water into an invisible gas, water vapor. Second, condensation. As that warm, moist air rises, it cools off, and cold air can't hold as much moisture, so that vapor condenses back into tiny liquid droplets. And finally, step 3, those little droplets need something to cling to, so they grab onto microscopic dust particles floating in the air, and boom, you have a cloud.
So you have these clouds just floating around, full of these microscopic water droplets. Precipitation happens for a really simple reason. Eventually, the droplets start bumping into each other and combining, getting bigger and bigger and bigger, until they're just too heavy to stay afloat. Gravity wins, and down they fall. Now, our weather engine has 3 main ways of making this happen. The first is convectional rainfall. This is just raw engine power. The sun intensely heats the ground, and that hot, moist air just shoots straight up. It cools rapidly, condenses, and you get a massive downpour, often with thunder and lightning. You see this a lot in equatorial regions. The second type is called orographic rainfall. This is what happens when the engine's gears, the wind, smash into the landscape. Moist air gets pushed toward a mountain range and has nowhere to go but up. As it's forced to rise, it cools, and it basically gets squeezed like a sponge. All the rain gets dumped on one side, leaving the other side of the mountain completely dry in a rain shadow. And finally, there's cyclonic rainfall. This is what happens when 2 different air masses collide. You get a warm, moist air mass running into a cold, dry one. They don't mix. The lighter, warm air has forced up and over the heavy, cold air, and as it rises, it cools and produces that steady, widespread, dreary rain that can sometimes last for days. So, there you have it, the great weather engine. It all runs on this delicate balance of heat from the sun, the pressure changes that result, and the constant cycling of water. It's a powerful, elegant system that literally shapes our entire world. Which, of course, leaves us with one last, pretty important question to think about. What happens to the whole machine when you start to change one of its fundamental parts?